Alright, so today I'm going to teach you about inflection points. Now, let's kind of review what we know. Where our function is equal to 0, we have an x-intercept, or a root, or also called 0. Where our derivative is equal to 0, we have what's known as a critical point. That's our maxes or mins, or sometimes neither. And then, where our second derivative, where the derivative of our derivative is equal to 0, that's where we have a point of inflection. Now, a point of inflection is where a curve changes concavity, which basically means how fast the rate of change is changing. So that's the rate of change of the rate of change, which makes sense because it's the derivative of the derivative. Alright? So the best way to think of concavity is like this. Instead of concave, convex, which is how we usually use the terms, in calculus we use the term concave up and concave down. Now, concave up is where your second derivative is positive. Alright? And a function that's concave up will look like a bowl. It'll look like a U. It'll look like a valley where you could pour water in and it would hold it. So that's concave up. It's a smiley face. It's positive. It's happy. So that's where our second derivative is positive. Alright? Concave down is a frowny face. It's down. That's where our second derivative is negative. It's negative, so it's down. It's sad. It's frowny face. Okay? If we pour water in, it will not hold water. Inflection point is the point where your curve will change from concave up to concave down, or from concave down to concave up. Alright? So let's look at this graph here. So looking at this, we should be able to identify which regions are concave up and which regions are concave down. Now here, from all the way over here till about here, it's concave up. It's a smiley face. We poured water in, it would hold water. So we know that this region is concave up, which means that we know that our second derivative from here to here has to be positive. Alright? And here our concavity changes from concave up to concave down. And it'll be concave down from here till about here, right? Because over here again it's concave up. So if our concavity changes, then that means we have an inflection point at here. Let's call it point A. Alright? Now, here, our concavity changes from concave down to concave up. So here we have another inflection point at, say, B. Now here it's concave up, and then somewhere around here it'll be concave down. All the way till somewhere over here. And here it'll be concave up again. So I'm not just picking these points arbitrarily. These are actual points. Okay? If we looked at this curve analytically, I'm not really sure how to make this curve analytically, but if we looked at this curve and we took the derivative and then took the derivative again, so we have the second derivative, and we tried to find the zeros of that, I guarantee that we would have zeros at here, 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 and here. And you can visually, and so that's analytically, and you can graphically notice points of inflections where you can see, okay, it's curving up, and then here, wait, it's curving down again. Okay? Curving up, and here, wait, it's curving down again. Alright? So, let's make, kind of summarize our general rules, is if our second derivative, f prime prime, is less than 0, so if it's negative, then it's concave down, frowny face, it's down, it's negative. If our second derivative is greater than 0, or that means it's positive, then it's concave up. It's positive, it's a smiley face, it's concave up. And this seems kind of common sense, but I just need to say it, is if our function, if the second derivative of it is equal to 0, then f has no concavity, or zero concavity, which means that it's pretty much a straight line, right? So let's try to do an analytical example of how to find the points of inflection of a curve. So say we had the function f of x equals x cubed minus 3x squared plus 3. Okay? Well, we can use quadratic formula. I used the zero function on my 89. And we know that f of x equals 0 at x equals negative 0.08, 1.3, and 2.5. Okay? Now, I'm not really going to show you how. You're not here to learn that. You're here to learn about inflection points. So, we know that this graph has zeros here. And let's take the derivative. So we'll get 3x squared minus 6x. So that's f prime. And we know that this has zeros at our derivative, f prime of x equals 0 at x equals 0 and x equals 2. Right? So that means we have critical points at x equals 0 and x equals 2. Alright, so that's good to know. What else can we tell? Well, let's take the derivative of this. So we'll do power rule 6x minus, well, 6. We know that this equals 0 at x equals 1. Alright? So that means what we know about this curve is that we have an inflection point at x equals 1. So it's going to change from concave down to concave up, or concave up to concave down. Now, how do we know which way it's changing? Well, we take a look at the way we would draw it is we have our function and our second derivative. Alright? And let's pick a point here where this is a known point of inflection. This point here. And, well, what is this point? Well, we know there's a point of inflection at 1, so at x equals 1, we know that it's going to change from concave down to concave up, concave down to concave up, or concave up to concave down. Okay? So we just need to check and see, is our second derivative of our function positive or negative on each side of the thing? Well, to figure out if it's positive or negative, we'll just pick a value on either side of our point of inflection and see if it's positive or negative. It's pretty kind of plug and chug. So let's pick a easy number less than 1. So a good easy number would be 0. So if this function here is 0, f prime prime of 0, that's 6 times 0, so that'd be 0 minus 6, which is just negative 6. So that means it's negative. Okay? And don't get ahead of yourself. Just because this is negative doesn't mean this is going to be positive. Okay? It's very possible that our second derivative comes up to the x-axis, is negative, negative, and then drops back down, only being tangent to the x-axis and not crossing it, actually changing and indicating a no change in concavity. Okay? So now we know that this side is negative, and let's pick a number on the other side. So let's pick, I don't know, some really big number, 100. Okay? So 6 times 100, that's 600, minus 6, well, that's definitely a big number, a big positive number. So this is positive. So our f prime prime is going from negative to positive. So that means it'll be going from concave down to concave up. And that's how you use, this is called the second derivative test, and that's how you use points of inflection and concavity to know about how your function behaves when you're graphing it.